Hey guys, it's Dr. Brown with Kubo Math coming to you from Tarlac City, Philippines. And tonight we're discussing Calculus 2, the fundamental theorem of calculus. So let's get after it. Okay, the fundamental theorem of calculus says if I integrate f of x dx from the limits a to b, it's the resulting integral of that f of x. So you can see the denotation by large F or big F of B minus big F of A. So I'm inserting that limit B into the resulting integration and subtracting that same integrated formula by inserting A. So how would that work? Let's say I have the integral of x squared dx from x equals, let's say 1 to 3. Okay, and that pen looks like I don't know if you can see that, it's a little bit light. Let me change that out. Okay, so let's integrate x squared. So we have x to the second power plus 1 equals 3, divided by that 3 or multiplied by 1/3. So the results would be 1/3 x cubed, and we're going to evaluate that from 1 to 3. Okay, so now we're going to take and insert the 3 into that formula. So that would be the big F of B. So we have 1/3 3 cubed. 3 cubed. Okay, minus 1/3. Yes, I know I could have factored the 1/3 out, but just to see all of this. 1/3 and put the 1 in. 1 cubed. Okay, so now I have 3 times 3 is 9, times 3 is 27. So I have 27 over 3 minus 1 cubed is 1. 1 times 1/3 is 1/3. So the results would be 26 over 3. That would be the resulting area under the curve from looking at this from x squared dx from 1 to 3. Of course, and you know x squared looks like that. So we're saying we're going from 1 to 3, so we're looking at that area right here, if this were 1 to 3. Okay? So that's the way that works. So let's look at a few graphical representations of the area and see what we can do with it. You'll notice this function is f of x equals 4. And it's defined from 1 to x equal 1 to 3. Well, what's the 3 minus 1 is 2. So the length of this side is 2. The height of it is 4. So one would think the area equals 4 times 2. So the area of that triangle or that rectangle equals 8. Okay, I should be able to integrate that function. So we have the integral of 4 dx from x equals 1 up until 3. 1 and 3. And you always put the smaller number here and the larger number there. If you go the other way, it'll be negative. Okay, so let's integrate that. That would be the integral of 4. You could pull that constant out, which is one of the rules. The constant k times f of x dx, and the integral of that is the same as taking that constant out times the integral of the remaining function. So we're integrating dx from 1 up until 3. So you know the rule integral of dx is x. So the results of this is 4x from x equals 1 up until 3. So now let's insert x equals 3. So 4 times 3. So we just worked with this function. Now let's subtract. Work with the other limit, 4 times 1. 4 times 3 is 12. Minus 4, oh, look at there, equals 8, which we should have gotten. So that's how the fundamental theorem of calculus works. to perform an integral. So let's keep rolling here. Let's look at this function. When x equals 0, f of x equals 2. When x equals 3, 3 plus 2 equals 5. So when the function is x plus 2, so 0 plus 2 is 2, 3 plus 2 is 5. So, hey, you know, we could, if we wanted to later, we could take and look at that rectangle, the area of it, and then the area of the triangle, and see if we get the same results by adding those together as we would get by integrating x plus 2 dx from x equals 0 up to 3. Hey, okay. So we have the sum difference rule when you're performing the integral of f of x plus g of x. It's the same as the integral of f of x plus or minus the integral of g of x. Same as what we did in the differentiation classes by looking at the sum difference rule. Recall the derivative of the sum of two functions was the same as the sum of each derivative. So if I have f of x plus g of x and the derivative of that, it would be the same as f prime of x plus g prime of x. Same here. Integral of the sum is the sum of the integrals, or the difference in the integral is the difference of the integrals here. So I don't think I said that quite right. So you're taking f of x minus g of x and having that as a difference, and then you're integrating the resulting difference. It's the same as integrating each individual function, then subtracting them. Okay? All right, back to this guy. Let's integrate this, x plus 2. We could break it out as we said here, but let's just for now leave it together. So we would have x to the first power here plus 1, and that equals 2. We'll divide by that 2, plus 2 times the integral of dx, which is x, and we're looking at this from 0 to 3. So we have x squared over 2 plus 2x from 0 to 3. So let's work with this side of it. So let's plug 3 in. So I have 3 squared over 2 plus 2 times 3. Okay, that worked through this and that limit, minus, well here we are here, minus 0 squared over 2 plus 2 times 0. Hey, all of that is 0. So we end up with 9 over 2 plus 6. So that's 9, we get a common denominator here, plus 12 over 2 would equal 21 over 2. So that's the area under that curve from 0 to 3. Now then, let's challenge ourselves by looking at this with just the areas of these two, the rectangle plus the area of the triangle. So the height on the rectangle here is 2. The width of this is 3. So the area on this square, this rectangle, a sub r, equals 2 times 3, and that equals 6. Okay? When x equals 3, f of x equals 5. So this point here is 5. This point is 2. So the height of this side is 5 minus 2 equals 3. Okay, so the base is 3. So now the area of that triangle is 1/2 the base times the height equals 1/2 the base, which was 3, 3 minus 0, times the height, which was 3, and that equals 9 over 2. 3 times 3 is 9 divided by 2. Oh, okay, so what do we have here? 6 plus 9 over 2. 6 plus 9 over 2. Or 9 over 2 plus 6. And that equals 9 plus 12 over 2 equals 21 over 2, which is what we had by integrating that. Obviously, you can't always look at these in terms of geometric figures and calculate it, because the function may be some crazy looking something. But when you can, it's easier to do. Now, however, like absolute value, integrating an absolute value, I personally think it's easier to do it in terms of the geometry and just looking at the shapes and getting the areas, because they're always a triangle of some sort. Okay, all right, let's keep rolling here. Hopefully everyone's been studying their math. Study, study, study. All right, let's just work a few problems just to get a feel for this. Okay, we have the integral of from 1 to 2 of x squared minus 3 dx. Okay, so integrating that, x to the second power plus 1 equals 3. Divide by 3 or multiply by 1/3 minus 3 times the integral of dx, which is 3x. So we have 1/3 x cubed minus 3x, and we're evaluating that from 1 to 2. That's very similar to the problem we just worked. So let's work on this side with the limit 2. So we have 1/3 times 2 cubed minus 3 times 2. So that worked through this section with that limit. Minus, so now we're here. And let's put our limit of a in there. So a is 1, so 1/3 1 cubed minus 3 times 1. So 2 cubed, 2 times 2 is 4, times 2 is 8, so I have 8 over 3 minus 6. Minus, I'll distribute the negative inside, minus 1/3 times 1 cubed, which is minus 1/3, minus, or negative times a negative is a positive, so plus 3. Okay, so that equals 8/3 minus 1/3, which is 7/3. A negative 6 plus 3 is a minus 3. So that equals 7, we'll get a common denominator of 3, minus 7 minus 9 over 3, which is negative 2/3. Now, you may be thinking, oh, whoa, wait a minute. You said we're getting the area under the curve. Yes, I did. Okay, so hopefully you can see this here. What is our function? X squared minus 3. So if this were just x squared, it'd look like that. X squared minus 3 says when x equals 0, I'm setting here at a negative 3. So we're evaluating that function from 1 to 2. So all it amounts to is the area underneath is greater than the area that was above that. So that's what that means. It's a negative area. There's more underneath that axis than above. Okay? All right, let's take and look at one or two more here. All right, we have the integral from 1 to 4 of 3 square root of x dx. Okay, so that we could restate that as integral from 1 to 4 of 3 x to the 1/2 dx. Use our constant rule here. Pulled the 3 out. Changed x, square root of x to x to the 1/2. Okay, so now x, we have 3 times x to the 1/2 plus 1, which is 2 over 2. So that gives me 3 over 2. I'm dividing by 3 over 2, which means I'm multiplying by 2 over 3. Okay, these 3's will cancel, so this equals 2 times x to the 3/2. And we're evaluating that from 1 to 4. Okay, so that's 2. Oh, and before we start, 3/2. What does that mean? You remember the rule, a to the m raised to the n is equal to the a to the m times n. Okay, so we have here a to the 1/2 raised to the 3rd power. So if I take 3 times 1/2, I get 3/2. So I could say this is the square root of a cubed. And that's how I'm going to approach that here. Rules, rules, rules. Okay. So I actually have the square root of x cubed. So 2 times square root of x, and I couldn't have written that any sloppier. Okay, 2 times the square root of x cubed. And we're evaluating that from 1 to 4. So 2 times square root of 4 cubed minus 2 times the square root of 1 cubed. So the square root of 4 is 2. 2 cubed, 2 times 2 is 4, times 2 is 8. 2 times 8 is 16. Square root of 1 is 1. 1 cubed is 1. 2 times 1 is 2. So 16 minus 2 is 14. So if I integrate 3 square root of x dx from 1 to 4, that area is 14. Okay. Last one. And I actually at some point in time, you guys know I have spinal stenosis, so I can't stand up very long. That's why I'm doing these 10 or 12, 15, maybe 20-minute videos. I really wish we could go and just work 30, 40 intervals, but I can't seem to stand up that long. So sorry for that. So we'll keep doing a few, and you just keep looking at the videos and let me know some areas that may be of concern to you, and we'll try to work through them. All right, here we go. We have secant squared x dx, and we're evaluating that from 0 to pi over 4. Okay, how many people, just scream into your monitor, what's the degree angle of pi over 4? 45 degrees. Back in the day, prior to use of calculators so much, pi over 4, well, that's 45 degrees. So if I have a triangle, pi over 4, 45, 45, 90, so this is pi over 2, we would know 1 square root of 2, that would be the lengths of the sides. And you think, well, how is that? Well, you have a squared plus b squared equals c squared. Remember? Side squared plus side squared equals the hypotenuse squared. Well, 1 squared plus 1 squared equals square root of 2 squared. Well, this is 1 plus 1 equals 2 squared is 2. 1 plus 1 equals 2. So we would know that if somebody said, what's the sine of 45 degrees? Well, sine is opposite over hypotenuse. We would know that's 1 square root of 2. Okay? What is the cosine of 45 degrees? Well, it's adjacent over that. It's also 1 over square root of 2. What would you think about pi over 6? That's 30 degrees. Well, that triangle would be 1 square root 3, 2. So this is your 90 down here, so this is 60 degrees there, or pi over 3. So if somebody said, what's the sine of 30 degrees? Well, it's 1/2. Okay, so having said that, there's one other thing I need to discuss here. Know your derivatives. You should know in a trig identity, you know, there's sine, cosine, tangent, and the inverses of all of those. Well, the derivative of tangent is secant squared. Secant squared x, or if I say sine theta, of course in this case we're looking at x. So the derivative of tangent x is secant squared x. So when I'm integrating secant squared, I immediately know that is tangent x. And we're evaluating that from 0 to pi over 4. Well, I now have tangent of pi over 4 minus tangent of 0. Well, what is the tangent of pi over 4? It's the opposite over adjacent. It's 1 divided by 1. Well, that's 1. Tangent of 0 is 0. So the resulting integral of secant squared x dx is tangent x, and from those limits 0 to pi over 4, the answer is 1. Study, study, study. Eventually I'd like to start a trig set of videos. As an engineering guy, trig was super important. Trig, algebra, differentiation is super important, looking at the rate of change of things. Integration, area under the curve, they're all useful. It's the concepts of calculus are super important to your engineering career. Now, ultimately, you'll have software to run a lot of things, but you really have to know what's happening when you plug those numbers in. And then many times, leaders, I used to have a guy when I worked for a certain company, they would come to me and ask, Steve, I need to know how those calculations work so that we can know when we sit in front of the CEO exactly what we're talking about. So many times you're working the math associated with that, trying to say, yes, that was a maximum likelihood estimate or some derivation, and putting that in depth. And that was the cool part of my job, I think. So I try not to lose these skills. Now, there's a lot of smart people out there. I'm not one of them for sure. But I did my best, and we did a lot of cool stuff throughout my career. So, okay, enough said there. Hey, why are we doing this? Because together we want to build a better life, okay? Build a better tomorrow. And we're doing that through math. So that's all for tonight. Keep studying, and then we'll talk to you next time. So take care.